Because I thought all the equations take the input like d over d.
Yes.
So does it matter if we use radius or diameter?
It does matter, because you are working with diameter. So the problem is, I'm sorry.
Continue.
Yeah, the problem. So on your on the ratio that you're given in terms of radius, but once you want to plug it into the equation, you have to use the diameter, not the radius, because otherwise you're gonna get the wrong result, and that's what happened to me. So, so once you pick up a different ratio, you have to use either my recommendation is for you to use the radius in order to get the model that you're working on. Once you want to plug the equation, the values into the equation, use the diameter instead of the radius. So it's kind of confusing, but that's how it worked for me.
Okay, so Marco, now I think you finished your work. Are you good?
I think I'm almost finished.
Okay.
I was working with my project, and I figured out that the reason that I was not getting the right result was because I was using the radius instead of the diameter on the equation.
Oh, in the equation?
On the equation. So
so the problem was in the equation, not in the output from the...
Yeah, the pressure is right, but I'm also, there's just a few issues where for the difference of the radius, the difference of the pressure, I got a different value. You have I think the difference of the pressure, because I have the theory and then you got the experiment.
Experiment, yeah.
So I think those are different.
Okay, so let's ask before you join us, was because we have, I think, 5 of you, and we want to make it like more organized. So let's have 10 minutes for everyone to just has a problem to let anyone share. I believe some of you need to share a screen. And also, as I said, I'm not like that professional in SolidWorks, but I think I can help a little bit. So all of you here, maybe also you share to solve, like maybe you have the same problem or you were in the same problem before, so you can help also. So let's start with, I think Naum, he was talking. So if you have something you wanted to share on screen, I will let you go and share it. And if you have like just only question, go ahead and ask me so I can answer. I think you said something about the streamline.
Yeah, that was the first one. It's just I straight up can't do it, and I don't know what to do.
So first I wanted to ask, did you like set your model and run, and you get you find like the K, and compare it with the equation? Did these steps? You only have problem with the plot, or your like output wasn't correct?
That's another thing that I'm still trying to figure out.
So I would say for everyone, how this is how the project has to be going. Okay, first you need to run your simulation, and let's later I will talk about how to do that and what's the most important. So you will run your simulation. You will get the pressure at the inlet, because at the outlet is given, right? So it's like the environmental pressure. Now you have an equation, right? So you wanted to create an Excel sheet and set all your input, and use the Excel sheet. When you have your output for the pressure, static pressure or average pressure at the inlet, use the Excel work. Also you can use like pencil and paper, and your calculation, but I prefer to be more organized to use Excel work. sheet and find. You ask to find what K? I think the losses, right? Then you wanted to compare it with the other with the Moodle chart, with the so you have to get like your value that you get has to be so very close with the equation one. You have also another equation. I'm just trying to get the file. Sorry, I have to have this file with me now, but I was like working and I didn't mention the time until the last minute. So I'm not sure if all of you went through these steps yet. So before, when you say that I have problem with the streamline, okay? Did you get, do you know that your work is correct from the beginning before you know you have problem to blot, away from the blotting? How do you know that your work is correct?
Because I've been able to get all the other plots in. That's the only plot that's giving me issues. But yeah, I'm also. I guess we can wait on the streamlines and.
Can you show me? Can you share your screen and show me?
It's still disabled.
So I don't know what to do to help you with this. I cannot see what is the problem. So I just wanted you to confirm that your work is correct.
You have to go into the meeting
did you find the pressure at the inlet or not?
You have to go in the meeting settings, Iman, and enable screen sharing. We can't screen share.
Who wanted to share?
Nobody can share.
You wanted to share?
No one can share right now because it's disabled.
Yes, I know that no one can share now until he tell me that I can share, because he said that his work is not ready. So I just tried to see what can I do for him. Then I will move to the other.
I think he means though he was gonna share, but it's still disabled. Like he can't share.
Oh, sorry, I didn't hear you. Okay, I will let you share now.
Well, oh Jesus, because I was about to load in my results and it just didn't. Okay.
Okay, now you can. Go ahead.
Cool. So, SolidWorks is being done with me. I can at least share my Excel sheet.
Mm-hmm.
Yeah, so my CFD stuff is crazy because my pressures are crazy because bad stuff. I was just talking to Marco about it, and it turned out that the pressures I'm using are actually the wrong ones. I'm using dynamic instead of normal pressure. But now I'm trying to get.
So the K epsilon you get is like -5, which is like
crazy.
Cannot be true. Yeah. So it's something here. It's about probably because you didn't add anything. Everything goes normal except the only information that you get from your simulation is the pressure, right? V1, right?
Yeah, it's the only thing I need.
Yeah, this one is not correct.
Yeah, I mean.
So can you show me, or your SolidWorks is not ready now to show me?
Yeah, because I tried loading it in, but apparently couldn't load in. Like it was working yesterday. 1 second.
Okay, so take your time.
Oh, I need to press solve. Okay. Yeah, we can go to somebody else.
Okay, so take your time until you make your. So can you stop sharing so I let the next student?
Of course.
Okay. So Lori, you want to go for next because I know that you have a lecture now.
Yeah, thank you.
Sorry for the others, but I think Lauren has a class now, so I will try to help her. So,
It still says that screen sharing is disabled.
No, it's open now. Okay. You can go share.
No. It's not working for my one computer. I'm sorry. Hold on. Let me sign out and sign back in. I'm on 2 computers right now because I have SolidWorks on one computer.
I think you can connect with your computer and computer lab at the department or the CU in general, right? Because I think There is SolidWorks in every computer in CU Denver. So if you didn't like download the SolidWorks, you can go and like connect with with the computer lab. I think, yeah.
Yeah, I have it. I just have 2 computers, so I'm on 2
Okay.
computers right now.
Mhm.
Okay, so
Okay.
I got it right here.
Mhm.
And screen sharing. Oh my gosh, it still says I can't screen share.
Why?
I have
I add you as a co-host.
Oh,
I
I think you have to add the one that just says Lauren, not the one with my picture.
Oh. Okay. So, okay. Yeah.
Okay, there we go.
Mhm.
So I'm just trying to set up my boundary conditions,
Mhm.
and I don't know what I'm doing wrong.
So I see that the computational domain itself is not correct. Why the computational domain it doesn't include? I mean, can you make it smaller so I can see your model? Where is the inlet? I mean yeah, I know that's the inlet, but I think it's like the tube has to be 2 sections, right? So you have 2 sections inside the tube. It's not like one tube. You have to have like we need the flow to go to a sudden expansion, right?
Okay.
So the design itself is not correct. This inlet for the first part has to be like small d, then the diameter is changing, right?
Well,
So
that's
you
what I
have
thought I did because I made the diameter bigger here than it is over here.
no.
Lauren, you might have to change your transparency so we can see the inside of the actual model.
Okay.
Yeah, so right there, yeah.
No, it's not correct. Your model doesn't. So it's okay. Me too. I don't know how to set it. I will say frankly because I'm not like using it. But I just will let you know that the shape you have to you remember the sudden expansion problem?
I honestly I've had to miss quite a few classes because I've been dealing with a personal emergency.
Okay.
But
So the sudden expansion problem, I need to I think. Okay, I'll show you something. Okay. So
Hey, Lauren, if you look at the book, I think if you look at the instructions for the model, if you look at the figure, I forgot the figure number.
622.
622. You look at that, you can see how the model is. It has a small inlet, and then it has like let's say.
Okay, so, if you see now, I will try to share it very fast with you. So it's like the camera is not like sitting in the. So I will show you. This is the problem you need to do. See here?
There you go.
This is the cross section here. You have to accept. I mean, you have to small like diameter here. Then the diameter become bigger. But in your model, you need to make this one like shorter here, short, and start from here. This is the model. So at the beginning, you didn't set the model correctly. If someone of you guys can like help her now, just like open your mic and feel free because I'm not like.
I could share my screen and show her how to do it.
Okay, who are you? Sorry.
I'm Diego, but let me log into my computer. Just 1 second.
Okay.
I already have mine open if you'd like.
Aiden, I think, or Alex.
Yeah.
Alex. Okay, I will make you go ahead, host now, and go ahead. Give us a lecture in SolidWorks.
I don't know about a lecture, but so basically this is the model that I have right here, where this is the inlet here in this section here, and then it expands out to a bigger diameter right here, but the outside diameter is all just this.
How you made this one at the beginning? So show her.
So what I did is just beginning at when you're creating your part. I started with a simple sketch.
Mhm.
Oops. Right in the beginning, and then just extruded that out to. I did it to 0.06 long, pretty much. So I have the outer diameter, and then the inner diameter. Extruded it out, 0.6.
So
And then from there, I just
it's important to make the first part is so short because you want to let the flow to go to the fully developed. You don't, if you make this part at the beginning long, that will cause some problem at finding the pressure at the end. So the setting that he did now, I mean, this shape is so good. I think you will get a very good result with this shape. Okay.
Okay. Thank you very much.
Okay, so Lauren, you wanted to set your model correctly, then I think you will not have any problem to set the boundary condition.
you
Start work.
underestimate me, but yeah.
Start working now,
Thank
okay?
you.
Or
You can hit up the chat. We got the fluid chat if you need to ask questions.
Perfect.
Okay.
Thank you.
Okay, who else have some problem or you need to discuss something? I mean,
I just wanted to oh, sorry, go ahead.
Who's who?
You can go first, Alex.
Go ahead.
I just wanted to discuss my cut plots and
Yes,
kind of to
yes.
see if they were like correctly done.
Okay, go.
Okay.
You set the boundary condition and start simulation or not?
Yeah, I started my simulation already. It's already
Okay.
been run and everything.
Okay.
This is my velocity.
Okay.
This is my
Can you make it like
yeah.
I can see the velocity, so yeah. Okay.
So I have it as streamlines and vectors.
Okay.
This is my pressure. This is the one that I'm kind of confused on. I don't know if this pressure is done correctly.
I think it's good. Did you get your did your calculation yet? Because this is how you know if it's like correct or not. This is the only way.
Through the calculation.
Yeah, because you already have an equation, right? You have the equation that's given. So I will just show you. I think it.
Well, I think the question is that we can portray the different factors that you're asking for in different ways, and that's one of the ways. I think it's a contour.
Yeah, it's a contour.
Yeah,
And,
I mean, yeah, it looks good. It looks good for me. It like makes sense, but you know what? Even anything in fluid mechanics, anything if you wanted to like calculate, sometimes you have the correct like physics. It looks like, but you wanted to know if your like answer is exactly, you have to compare with something like analytical solution or so. This is how it works, right? So in this case, he gives you an equation, right? So he gave an equation. I think now I will show the equation in my camera here. We talked about this one before. I think if you wanna, okay. So here, this is the, sorry, because that was like discussion with one of the students. So don't look to this one. So look to this part here. So this is for the pressure known, for the pressure difference, right? Delta B, this is delta B. And so you have according to the ratio for the diameter ratio, you wanted to find this one. Also, you have this equation here, right?
Yeah.
So for this equation, everything is given except what? Except this one. This is what you are looking to find from your simulation. So when you run your simulation, find B1, the pressure at the inlet, and plug your what you get here, and find K epsilon.
Okay.
And go ahead. If you get and you have the Moody chart, right?
Yes.
So for the Moody chart, you can for the same information you get K epsilon, and if your answer is so close to what you get from the Moody chart, that means your pressure here is correct. Your simulation is correct. But if you get like K epsilon, like let's say how Naum he get like -5, he's supposed to have like between 0.56, I think, 0.5 in this range, right? So if you get like some your output or your what you calculate is like doesn't make sense, that means even you see to the simulation and you feel like it's good, makes sense, but still you have something is not correct. Like if you get the output as the dynamic pressure, not the average pressure, so all this can like affect your answer. So what you're supposed to set in the final report is your calculation, okay, and you have to submit a chart, right? You ask to find the chart, compare K epsilon at different D over D, right? This is what he asked you, I think. So this is, let's say, what you get from the Moody chart. Your answer has to be so close. Okay. So this is so I think now, Alex, what I saw now in your work, it looks good. I believe that I don't think that you will have any problem to find the correct answer. Go ahead and finish the calculation. Check if you find that your answer wasn't correct. That means maybe you need to make like the YouTube more longer. You did some mistake in the output, like you choose find the dynamic pressure instead of the static or the average pressure. So just go ahead and see what you can get.
Okay, thank you.
But it looks good. The pressure and streamlines. First, the physics is correct.
Okay, thank you.
You're welcome. So, any who have
Can
another?
I ask a couple quick questions? Especially I have a lecture here in a second. But I was talking to the professor about this, and I guess I got kind of confused because I'm seeing a pressure increase from the inlet to the outlet, which I guess kind of defies logic a little bit. We should generally see a pressure decrease as flow goes downstream. Is that correct? Like, should we in fact be seeing a pressure increase in this particular part?
It's because you put the atmospheric pressure at the other end of the lid of the outlet.
I think it's because the fluid's getting slowed down.
Yeah,
so the pressure is the force that's slowing it down.
Expansion, yeah, right? So you have expansion.
So the pressure increase is correct then?
So you have expansion. That means the velocity is decreased. That means the pressure is increased. So the pressure at the inlet has to be less than at the exit, right?
Correct.
Yeah. So so you have expansion. So velocity is decreased. That means the pressure is increased. That means the pressure at the beginning has to be less than. So you have drop in pressure. You have increase in pressure.
Okay, yeah. That's what I'm seeing. But the professor said that was impossible, so it just kind of really made me question things.
I don't know. I can't. He's the professor, but I can't. He is like, but you know what? This is expansion. I mean, no. The pressure, the velocity is decreased, right? Unless, can you show me your work? I wanted to see the flow, so I can like.
Can you let me share my screen and I'll share it. I'll let you see the part.
Okay.
Do the other one though. That's still muted. It's on my other computer. The other Michael.
You are Michael. I add you as a host, I think.
Let's see. Do my other entry. I'm sorry, the other Michael Roseberry that's appearing on the partition.
Okay. Yeah.
So how close should our CFD be to the estimates?
So show me the pressure.
Sorry.
And those streamlines that you see are pressure streamlines as well.
Yeah, so I can note that the pressure become like the exit become red, which means that increased, right?
Correct. Yeah, that's what I'm seeing. I just wanted to make sure, just because I guess it doesn't make much sense to me logically as I was working through it.
Yeah, it doesn't make sense. I think Michael, Michelle. Okay, someone. Okay, so I think Alex, before you, he showed some pressure contour, right? Alex, are you still here?
Yes, I did pressure contours.
So the pressure contour show me at the, it's like show that the pressure increase or decrease.
So for me, it shows an increase.
Yeah, which makes sense, right?
Yeah.
Yeah, Michael, something to consider is that if the fluid's slowing down, then you can think of it as a force pushing it back, right?
Yeah.
So the pressure is increasing because the fluid's slowing down. Because
Yeah.
if the pressure decreased more, then the fluid would be going even faster at the outlet.
Yeah. So I think you're fine, right? Because also you have the pressure increase, right, at the exit.
I mean, it's just atmospheric pressure, though. So I mean, it's the same pressure that the entire flow would be experiencing, no?
But
No, the inlet has a lower pressure because the fluid's moving quickly.
Has less space to move through, pretty much.
So did you show the professor this result or not? Did he say that makes sense or?
I did show him all of these images, and
you show him this image and he said this doesn't make sense.
Correct. Yeah, he recommended I speak to you because he thought my inlet conditions were set up incorrectly.
Mm-hmm.
But he said the flow should occur from the higher pressure inlet towards the lower pressure outlet. I think you may have set your inlet conditions incorrectly. He said the code should automatically develop a higher pressure at the inlet compared to the outlet, and the simulation should then become self-consistent. That's what he told me. And then he went on to say, it is not physically possible for the flow to occur from a low pressure side to a high pressure side if there are no other driving forces involved. And so I guess that's what's confusing me based on what he's saying, just because I've spoken to about 5 or 6 different people that are running these, and we're all seeing a pressure increase, and I think everybody here right now is confirming that. But Dr. Premnath, I guess his comments are different, so I guess that's what's confusing me.
Confusing me too.
Yeah, because he does realize that we're forcing fluid in, right? This is not like there's energy constantly being added in for this to work. This is not equilibrium at all.
Mm-hmm. You know what? He said that there is another force affecting the flow. Did he say that?
If there are no other driving forces involved, which in this case there are not. I mean, your inlet.
But there is. The inlet has a constant stream of water coming in, right? Mm-hmm. So from my understanding, we're assuming that some kind of force is pushing the water in the first place. That's my understanding of this.
So in this case now, in fluid mechanics, you cannot like say that there is another force. There is no another force, because whatever was the force, it's out of the domain that you work on. If you include that part, that at the force in your simulation, that means that will affect. But now we have like point A, point B. So we have to see what's going on between two these points, right? So let's say the flow is coming from the inlet, and it has we have an area, and we have volume flow rate, right? So that if we specified the area and the volume flow rate, that means we specified an inlet velocity. So the inlet velocity here is given. I mean, it's like, we know that the flow is like not coming hanging out. He comes from some other part, but it's not included inside your domain. your domain now is between A and B. You have to think about what's going on between 1 and 2. So the only thing happened between 1 and 2 is an sudden expansion. The flow comes with a velocity, specific velocity, and accordingly it will have an inlet pressure that we don't know about it. Okay, so it goes through the pipe. When the area changed suddenly, it has sudden expansion, which make the vortices occurs at the two edges that you see. Okay, so after that, because we choose the area to be so long, we want to ensure that the flows will retain again to it's like laminar flow. Okay, fully developed. It will be like have time until like all the turbulence because of the vortices goes away and the flow return back to go laminar at the exit. So at the exit, what I have a flow comes with the velocity. Let's just imagine like the sudden expansion happened. Now the area is wider, so the flow goes. You can imagine that, so you know that the velocity at the exit will be lower than the velocity at the inlet. This is like 100% happened. Okay, so since the velocity at the inlet is small, and you already have, you know that your flow goes to be exposed to the environmental pressure, which is known. Okay, so in this case, the pressure at the inlet, it will be lower than at the exit. This is my how I can explain this problem. But if he said that he expects the pressure to the inlet to be larger than at the exit, I don't know. I have to check that actually.
I spoke with the professor about a week ago, and I showed him the model. He never said anything about the pressure being. Well, he never said anything about my model in terms of the pressure. So I don't know if he's well, I don't know what he's in terms of what I can't talk. What's wrong with me? I don't know if he wants to something specific, or I don't know because.
Okay, I will show you something now. I will discuss this together to see if that's maybe explain more. Okay.
Okay. Yeah, I guess I'm just gonna assume that the pressure
So
increase.
let's say to sorry, let's look to this equation here, this equation. Okay, look to this equation here. So this equation describes it's the pressure will change according to the change in the diameter. Okay, so here we have sorry, can you see the equation now?
Yes.
Yes.
Okay, so D2 is now you have D1, D2. So when he gave you the information, which D1, so D1 is greater than D2, right?
Yeah. Wait.
Okay,
Yeah.
so according to what he means by D1, D2, if he means D1 is the inlet or the outside diameter, so that means B2 will be greater than B1 for sure. Because if D2 less than D1, that means this one will be a negative sign. So okay, that means B2 equal B1. Okay, so if this one become negative, that means this minus some value here, which is equal multiplication of this. That means B1 become B2 will become less than B1. If this one was positive, that means we have increase according to the equation. I just I explain what I think about how the pressure increased or decreased. Usually, if we have like we have a nozzle, let's say we have a nozzle. So let's say for airplane or something, okay? So if we have here Q1, V1, and A1. And if this area here, we have B at 2 is equal B atmosphere, right? And A2 is greater than A1. But you know what? I explained this one according to my understanding, but if the doctor adds some information that I don't know, like he said, like there's why he expects the pressure to increase. He said that he will increase at the exit, right? Decrease, right?
Let me pull it back up. Let's see.
Maybe you didn't understand what he said. Maybe he said that.
Oh no, I just read it verbatim. Yeah, the flow should occur from the higher pressure inlet towards the lower pressure outlet.
From the higher pressure to the lower pressure. So B1 is greater than B2.
Correct. Yeah, that's what he's saying.
Okay. So all of you in your simulation, did you find that B1 is, did your simulation show that B1 is greater than B2? Or you have that?
I don't think a single person has experienced that. I think everybody's experiencing P1 being less than P2.
Yeah, my contours show that P1 has a lower pressure than P2.
Yeah, I'm showing the same results as well.
Okay. So just continue what are you doing, and I will discuss with him again. And
Okay.
you know,
We misunderstood or something. It seemed very explicit, but I'm just gonna go with what everybody else is seeing.
yeah, if he has some point, I will discuss with him and let all of you know. But I mean, just if you okay, let's say, did you finish your calculation and get K epsilon, and you find that you are close to the experiment or not?
I have not calculated it yet. No, I wanted to confirm this before proceeding.
Okay. So if you have finished your calculation and find that your answer is so close to the experiment, that means you are good. Don't care about it. I mean, I don't mean don't care. I just like you are good. But if you have some problem, that means maybe we missed something that he knows and we don't know. So I can't say now. Actually, I have. Okay, I was looking to. I have some example. Okay, for the last year project. But I was all the while I'm talking to you, I'm trying to find it, but I couldn't find it in my office. So I will go direct and see in my computer. Okay, if I find it, I will show you. I will share with you. So I think that will be. Okay, I think we have something here. Okay. This one. Just say me. I think I can answer you now. So let's know what's the problem.
I think the pressure on the inlet is right because I just went ahead and did the calculations for the K expansion. And for the theory and for the experiments, I got a very similar result.
Oh, so you did the calculation and find similar result. That means your work is correct.
Yeah, as well as the pressure, the pressure difference. I also just I just obtained a very similar result too. It varies by some numbers, but it's kind of in the same range.
Okay, so I will.
Thanks, Marco.
Use some like
No worries.
previous work from. Okay,
All right, I have to
pressure contour. I will share now. Okay, can you let me share?
Okay.
because this will at least will explain what's going on. Sorry for interrupt. So I think. Can you see this my screen now?
Mm-hmm.
Yes.
So this,
Similar.
yeah. So this is the previous result, okay? And you can see that the pressure goes from blue to red. Red here, the colors is not like clear enough for me, but it's like I think it's clear that it goes the red one at least at the end, so the pressure goes to be increased at the end. And I will try also to see another example. Oh, no, this one. This is dynamic, I think. Okay, so
Ooh. I just took the screensaver.
okay. So let's go down. Okay. Okay. So this is. I mean, this is by the way. This is different. Different ratio. I mean, for there's things that different in this work. I mean, you cannot like expect that it's the same work. Okay. So this is previous, and the problem was different. I mean, they check the change of the geometry and things, but you can see here. I can see that the pressure goes. This is the pressure contour also, in the sudden expansion, and the ridge one, the ridge area goes at the at the exit. Okay. So low pressure at the green one, which is here. Okay. So I think go ahead and work, finish your work as it is now. And since one of you like confirmed that he gets a good result, so I think you are good. Okay.
Okay, cool. Thank you. I appreciate your time.
Okay, you're welcome. So any other problem?
For me, I'm sorry, but Alex.
That was me.
Oh, I'm sorry. So yes, like we talked about before, this some
Yeah.
problem with the streamlines. So instead of the
Okay.
streamlines, I used the ISO lines. I think that's what it's called. It's very similar,
Okay.
the streamlines, but it's not the streamlines.
You wanna share? You wanna share what you got?
Yeah, sure.
Okay.
Let me go ahead.
Go ahead.
Thank you.
I think we have Diego here. I didn't hear from him. Maybe he has something. Oh, let's go after. Sorry.
Yeah, let me just
Mhm.
hide this. So, like I mentioned, I was trying to use the streamlines, and it keeps keep getting this error message,
Oh.
and it works
An
sometimes.
internal error causing hardware entries cannot use the event-based lines function.
Yeah, it works sometimes, then it doesn't work, and it works sometimes, doesn't work. So I stopped using the streamlines and I use the ISO lines.
By the way, I mean, like, it's not necessary to show the streamlines. Did he ask you to show the streamlines specifically?
Yes.
Oh, I thought he asked for the contours and
No,
vector.
he has contours, the vector, the vector velocity, vector, the streamlines, and turbulence.
Okay.
I forgot what it's called. Turbulence.
But I think the vectors,
Intensity.
specifically the vectors will show I mean, everything will show. Usually, like when I do the streamlines, I don't do the vectors. When I do the vectors, I don't do the because it's like showing the same. In case you have streamline, I would say that let this problem at the end. Finish all your work, and if you can get the streamline, okay. If you don't get, just let him know that I have some problem when I plot the streamlines. But if you show the contours and all your work is correct, I mean, I don't think that will make like that difference. But you said that you use something else, right?
I use the ISO line,
Okay.
and they're not streamlines, but I guess it shows something similar as the streamlines, but the streamlines have better resolution.
Yes. So go to the streamline again.
Mhm. And the streamlines, yeah. There you go.
So just say okay, and
now it's grayed out.
so this is streamlines or the ISO line?
This is the ISO lines.
Can you take it off? I mean, I just make like if you wanted only to draw the streamlines.
Let me see. Just display. Yeah, I know.
Okay. So
yeah, it's wants me to. No, I cannot even select the streamlines. It's grayed out now.
Mm-hmm.
And
just make sure that your boundary correct and you are like choosing the streamlines inside the closed domain. Okay.
So this is my domain right here.
Yes.
So my domain is within. Well, actually, the part is within the domain. But like I mentioned before, the streamlines work sometimes.
Did you increase the grid resolution and check
the grid resolution?
Yeah. How much grid resolution are you using now?
What is the grid resolution? Good question.
Go to the grid mesh for the mesh. Sorry,
mesh. This one right here, or the global?
Mesh here.
This one?
Yeah. Here, choose the second one section. You remember when we changed it? We did it before together. Are you?
So that
we did that before.
Yes, yeah. But it was actually the global mesh. It was not.
Okay, go to the global.
Yeah.
Even we have refinement, it's okay. Go to the global one. Okay.
So this is what I got so far.
I just suggest that maybe you try to increase the mesh resolution. Maybe your choice, like there's some, try to make them all equal.
All equal?
All of them, yeah, equal.
Okay. I'm guessing that I have to.
You have to simulate again.
Okay, so yeah, then I'll give it a try because it's gonna take longer.
Okay.
So yeah.
I will say someone else. I think Diego or so. I didn't hear from him.
Stop my share.
Who else wanted to share ours?
If Diego's not going, then I did switch out the pressure.
Okay.
Yeah, I don't think I need to screen share. It's just, is 0.618 considered close to 0.56?
Not that much. I need two more. It's good. I mean, at least it's not -5. Yeah, you're good. But you wanted to make try to increase the resolution, or I think you are so close. Since I mean, it makes sense, right? So maybe if you can show me your model.
Yeah, because my pressure is, I think it's around 100. Oh wait, I need to screen share. I have to do that first.
And don't forget that you asked also to compare the pressure from the simulation with the simple control volume model, which is you have in. So I mean, this is a very good key in your, so you know that you are working good or not. If pressure difference, as much you will become close to the formula, that means you are absolutely correct. Okay, so don't focus on only just simulation and go to do the computation step, because this is so important. Okay.
Yeah.
Yeah.
Yeah, I'm not
So,
fully sure what I'm showing.
Can you
because I got
show me? Can you show me the output? What's out the global output? The global
Like the-
result. Yeah, how to choose your result. Yeah.
maybe
Show me how you pick it. Sure that you pick the brochure.
because I got a different file for each ratio, and it's a little tricky.
No. This one. This one. When you at the beginning, when you set your project, when you go to the last step to choose what's output you wanted to see.
Yeah, you mean like the surface parameters?
Yeah. Show me the
Yes.
surface parameter.
Yeah, my surface parameter is lid 1, and I selected pressure.
Make this one. I wanted to see more for this one because the other I think Marco, if he's still with us, when you show the output, it's not like only pressure. You have pressure, you have bulk, you have average. So
Oh
which
yeah, that's all down here, right? Bulk average, maximum, minimum.
okay. So go to the you pick the average always here.
Okay.
Don't
Yeah, this.
don't take the bulk average, the average only.
Uh-huh.
Only,
Okay,
So
so
this, so
only
this is
the
the
average.
difference. Yeah, don't talk like an 92,900 here. Go here.
mhm.
92,800. So this is what you wanted to use in your computation steps.
All right. So just regular average, which is.
Yeah.
But as you can see, the numbers are very close to each other. The pressures are
Very
very
close, but it causes a difference between 0.65 and 0.56. I mean, just maybe you want to become like 0.58, which is good, I think. Try it. Give it a try.
Yeah, the only. Okay, because. I think this is. Why is it still. No!
Wow. So, okay, continue. What are you doing? If someone, I just get the chance for, I don't know who he.
Anybody else?
Anywho,
I'll stop sharing real quick.
I was wondering if I can show you my calculations real quick on Excel, super
okay.
quick, and I'll.
Okay, go to the super quick.
Okay, thank you. So this is what I got so far, and I'm just gonna adjust the pressure P1, which is incorrect. I need the average. So, but as you can see, I'm very close.
Yeah, this is good work. You still have to correct the pressure, right?
Yeah, I still have the correct pressure, which
Yeah,
is
so I think you'll be. Yeah, I think you are doing good. I mean, as soon as you correct the pressure, I think that will also affect the work here in the experiment. So this is good. You are doing great.
and the only difference is the experiment pressure and the difference experiment pressure and the theory.
Yeah, he asked that, I think, in step number 2. Yeah, he said analysis result. He said compare the pressure from the simulation with. You can add that as like take the percentage, okay? If you take the percentage, I said like we have an error of like 2% in between the pressure and the experiment and the theory while you explain your result, okay? Because he add that in the analysis results.
Okay. Gotcha. Okay, thank you.
Okay.
Okay, so one of the issues for me is that I can't reliably open my SolidWorks. I have multiple models open. It won't necessarily let me go to any particular one. So like that number I was showing you was for a different one, and so I tried putting that number in, It came out
Oh.
weird, but I haven't worked on that yet. So it's a hodgepodge. But what I want to ask, moving away from that, is when we're presenting this stuff, should we include all 4 plots for all 3 ratios for a total of 12 plots? Oh no. Because we also have the surface ones, so that would
Check
be
that.
18.
I will check that from the previous work because of that I actually asked for to see a previous work to understand what's supposed the student to show. So I think first you have to set the introduction to your work, then you show the method. So you talk about the solid work and how it's the diameter and how your model looks like. Then you go to the result. Okay, first he showed the pressure contour plot for sudden expansion with a D over D ratio of 0.2. Also, then, so he showed the streamline, the velocity field, which is the vectors, and the pressure. Then I think he repeat I think he expect that you wanna repeat show all your work here.
So we'll show every single plot.
Yeah, I will also share now to see you also another thing you need to, I think.
Any particular
You can show
rules?
also your work here if you can see my screen now. So it's just you see how if in as much as you change D over D, you show K epsilon for the theory, for the experiment, and for your work, and also for delta B. So this is how you show that the change. Okay. So I think this makes sense. I mean, this is give more out. You show your work more like efficiently. Okay. And as you saw here, he show everything for whatever he changed D over D. Also, this is how you change, how you say the plot that the doctor, professor said that you have to say.
So only the wait, what?
This is
Why
what I was talking about.
I'm a little confused. How come their experimental is discrete?
What do you mean discrete?
Oh, it's like 3 red dots instead of a line.
It is. Because for the experimental, you will go to the Moody chart, okay? You will go to the Moody chart, and you will have only 3, specific value. You will not have like a chart for the experimental part. But for the theory part, which is equation, you have a line, right? Because you can like make D over D change like even like 10 or 20 times and you get a line. This is from the equation because you have 2 things to compare with. You have an equation and you have experiment, right? Did you get that?
Yeah, it's just so because I think it's
when you go to the Moody chart and for a ratio of D over D, if you follow, you will get one value for K epsilon, right? So experiment is specific, 1, 2, 3. Your work is 1, 2, 3. But the equation, you will have a line for the equation.
So we don't need. So we just need the diameter ratio as a reference to go to the Moody chart and just get the K result. We don't need the what's it called?
You need that, I think, a Reynolds number, right? You can get that from the Moody chart, and you need to find. I don't have the Moody chart. Do we have it? Can you
I
share
do have
it?
yes,
Can you share it? Mm-hmm.
Of course. Let me go ahead and share real quick. No, this is not the one. Sorry.
Yeah, it's okay.
Yeah, because what's confusing me is, we have a figure we're supposed to work with, figure 622,
Mm-hmm.
and I thought it it showed a curve which was experimental. Like the curve was designed just to fit experimental data.
Yeah.
Can you see this?
Yeah. So I think he gave you the kind of buy. You are given that, right? No, this not this one. So not Moody chart. This is he talked about the figure 6.22. Do you have
Oh,
it?
6.2.
Sorry, I just like I did the mistake.
No worries.
Go to the figure 6.2.
6.2?
Yeah.
622.
622, 622, 622.
Let me give you the page number. For me, it is on page. Have you already found it?
Right there.
372.
Yeah. Here it
Is it 372?
So you see here. So for every d over d here, you will take the. Then you go to the sudden expansion chart here, and just go to find k. Okay, so let's say at 0.4, I will go up all the way. So I will get k equal like around 0.74 or 75, right? Are you with
If you,
me?
yeah, but if you scroll up a page, they'll give you the equation for that curve.
Yeah, you have to use the curve and you have the equation. No, the equation is not like for this. This is an experiment. Okay, and the equation is like different one. I think the equation he gave in the.
Oh no! If you scroll up the page, you'll get a different equation, which they claim matches with experiment. Could you scroll up real quick, Marco?
You don't. Yeah, you can use it. Go down. I will say that if this equation state.
Which one?
Oh, she's right. I'm sorry.
No, there's no equation. Yeah, you have to use the only equation you will use is the. He said that compare with the chart in figure 6.22 as well as the simple CFD model developed in class. So you remember at class, he solved this problem, and he derived an equation at the end.
Mm-hmm.
Okay, so go to your lectures, okay, and see the equation he derived.
Is this the one? Oh, no.
No, this is not the one.
Okay.
So I think
I'm gonna stop sharing.
I will go to the lectures. Yeah, stop sharing. So I think I'll go to the lectures. I will find that for you, okay? So you have, I think it's like.
She's wondering who's grading this?
Grading what?
The project.
I'm not sure. I hope not me. I think maybe, I don't know.
I feel like we're getting into a lot of situations where it's like the grader is right, like. So I just wonder who's adding.
He usually grade the exams, but I'm not sure if. So not this one. Try to find the lecture when he derived this one. I didn't like download all the lectures yet, but I hope that it will be somewhere here. Because I think Marco will find that talk about this equation before we.
I think we talked so many equations that I forgot pretty much. But I think. Let me see if I can find it real quick. Yeah, we talk about this equation. I don't download it. I cannot find it here for the download. Lectures, maybe it's like. So I think the lecture will be. If you go to your lecture before November 2nd, think I got the number second. Let me check real quick.
He derived some formula. He derived it, and he wanted you to compare that equations, which is the one that you will get like a line plot with this chart. You will get like spots, and your result also will be like specific value, right?
I think I found it. You want me to
Okay.
share it real quick?
Yeah.
Real quick, how did you guys get to show the average for the pressure instead of the bulk average?
So for that, let me show you real quick. I'm gonna share. So okay. Oh, still calculating. I don't know. So I think that's the surface parameters. You're going to in order to show everything. So it's not working for me. It's right click. And then I think it's right click and then it's not letting me. Can you share your screen real quick?
Who's sharing?
I am.
So, okay, so do you have, okay, go ahead.
I think it's on surface. I think it's the other one, the surface parameter one.
Oh, gotcha.
Edit definition. Then show. Yeah.
Oh,
there you go.
Thank you. Okay.
No worries.
Perfect.
Now you get the average and everything.
Okay. Thank you.
No worries.
Okay, so the equation.
Oh yes, let me show you the equation real quick. Is this the one?
Yeah, go down. You derive it. Yeah, go down. Yeah, I think this one. Yes. So this one at the end, so k is equal 1 minus d squared over d squared all d squared.
Mm-hmm.
Want to use this one and compare it. With,
Wait. The equation at the bottom is the equation he came up with?
Yeah, so you gotta use this one. This is actually a theory equation.
Yeah, this is the theory. Yeah, you can go and plot this one. You will get like a line plot, right? And then you add your foundation, like 3 spots, 3 like points. Add d over d, like specific, like 0.5, 0.8, 0.3. And also you have the experiment that you will get. You will find from the chart 622. Okay.
So
Compare them all in the same plot. And
so,
I should. Yeah.
But for this, so we have to plot this equation.
Mm-hmm.
And can we do it in Excel or?
This one, yeah, Excel. I mean, show like better result.
Okay.
Because of that, I said do your calculation at Excel, so you can add, like, have this one block, then you add like as a data, add data from your output or your solution as a data, adding data, so it will show like spots, right?
Oh, you mean for the different values that you obtain?
Yeah.
Okay.
So
yeah.
I would just because if you can stop sharing now.
Yeah.
Just or go again to. Starting here in this work here. Yeah, I will go. I will share it now.
Mm-hmm.
So I will share again this result from the other student. So this is what he expected, right? So this is the resistance coefficient K, and this is D over it. So you need to the line plot is the equation that he derived from for the sudden expansion. You will find it at your lecture. And these two is like, this is what he, CFD, what he find. And the red one is the experiment, okay? So that he got from the, I prefer, if I were you, I mean, instead of doing this, like for the student, it's better if like write here experiment and from figure 6.622, and this one like solid work, and this one an equation, okay? So that will be more clear, I mean, for the reader to understand what's this one is about, okay? Or what's this one comes from. Usually we refer to the reference inside the plot. So this just to like example to show you what the professor expects you to set in your report, right? So this plot is essential. Show also table for your results and show all the contours and vectors in 3 cases. And of course, explain what are you doing at the beginning and add your reference. This is all.
Okay, so just explain what we did.
Yeah.
And
So
pretty much
start with the introduction and the method and what you did. I mean, just a small report. I mean, I'm sure that you know how to write a report.
Not really. I'm just kidding. No, I do. Yeah. So yes. What was I going to ask? So yeah, I'm not very familiar with MATLAB, so I'm just gonna stick with Excel.
Yeah, Excel is good.
And
You don't need to set the MATLAB for this. I mean, it's just like you already have your result in SolidWorks. All you need is this chart, and I mean, Excel is the best tool in this case. There is nothing there is no work need MATLAB here.
Okay, but there's work in the homework, so I'm just gonna talk
yeah,
to
and
you tomorrow.
homework. Yeah.
I'll talk to you tomorrow. So I know
Okay.
you're gonna leave.
Thank you.
No worries. Thank you.
Okay. Bye.
Bye.
So, any other question? Still have 10 minutes for 12.
For little d over big D, that's just our diameters, like our inlet and our outlet, correct?
Yeah.
Okay. Yeah, that's fine. Okay. I think I should be good then. I'm just gonna continue working on it.
Okay.
Okay, thank you.
You're welcome. Bye. So I think Lauren has a lecture now. So now, do you have any other things? Did you start your calculation yet?
Oh yeah, because like you saw my calculations from earlier, right?
Oh yeah. And now you become like more closer, right?
Yeah. So I guess there's not too much I can do at the moment because my computer's just kind of being dumb.
I just like changed my computer now during the when I like went out. I changed the computer because that one was like almost like it's heat up. So I changed the computer now.
Good is this is not getting hot. It's just I click on SolidWorks and it doesn't go to SolidWorks. It goes back to Excel.
So now you get so close. I mean, at least you fix the main problem that make you like so far from true. I mean, -5 is something like it's not correct. But now since you get like a 0.65, let's say, and it's 0.55. So just tell me what's the ratio you are using now when you get 0.65? What's the diameter ratio? How much?